Hey everyone, I'm back. So I just finished Google Kickstart 2021 round E, ended up in third place, and now I am going to go ahead and go over solutions. I should note off the top here that I think the authors got the difficulty ordering for this round very wrong. A is the easiest problem, but I actually think D is the second easiest problem, then C, and then B is the hardest. You can maybe make an argument that C is easy, or that C is easier than D, but I don't know. Hard to say, but either way, B is the hardest. D is not significantly harder than C at any rate. So if you tried the contest and then you saw B and then you just got stuck and quit, definitely make sure to take a look at C and D because I think they're significantly more approachable. But with that, let's talk about the problems. I'm just going to go in order A, B, C, D. So problem A, we're given a string containing letters of the English alphabet, and we need to output a second string that's an anagram of our given string, but where the two strings do not match in any position. And it may be that this is impossible, and if that's the case, we should just say so. Now, this is a very standard problem. If you've been doing code forces for long enough, you've probably seen something pretty similar to this. So, if this isn't something you've seen before, it's a good construction to learn. I should start by noting that for the easy subtest, the length of S is at most 8. And in that case, a solution, or then you can just iterate over all permutations of S and see if one works. And if we define the length of S to be n, then that works in O of n times n factorial, which is fine for our purposes. But what we're really here to talk about is the hard subtask. So what I'm going to claim, this is definitely something that you should remember because it will come up again, is that the answer is going to exist, if and only if no letter appears in more than half the positions in S. I.e., if S has any letter that appears in the majority of positions, then it's going to be impossible, and otherwise it's possible. Now, we can see that if there is a majority letter, no answer exists. We can see this pretty easily, and the idea is that, let's say that our input string is S, and our answer string is T. And without loss of generality, let's just say A is the majority letter. Then, A appears more than n over 2 times in S and more than n over 2 times in T, so more than n times overall. But the problem with this is that A cannot appear in both S and T at the same position. So in a valid answer, A has to appear at most n times, so this is a contradiction. So therefore, if there's a majority answer, a majority letter, then no answer is going to exist. But now let me show you how you can construct the answer as long as no majority answer exists. And so the idea here is we're going to sort the letters in descending order of frequency. And then we're going to iterate over them in that order. And for each copy of letter I, we'll just take the next available letter J with J is greater than I. And if there's no such letter, then we'll just wrap around to the beginning of the alphabet again. So to give you an example of how that works, I'll show you the sample string. So we have start, and so there's two T's and then A, S, and R. So the ordering is going to be T, and then the order of the rest doesn't matter. Let's just say it's T, A, R, S. So now what we're going to start by just assigning the T's. And so the first one is going to get the next letter, that's an A. The second T is going to get the next available letter. There are no A's, so we would check R's, and there is an R available. So that's an R. And now we assign the A. So we check R, there's no R's available. We check S, there is an S available. Now we assign the R, we check S, but there's no S available. We've already used it here. And so this is a T. And likewise, this ends up being a T, and so we get this string taster. Okay. So that's what we're going to do. Sort of the general idea is that the next letter afterwards is going to be the one that appears most frequently among the remaining letters, and thus the one that's the most likely to cause problems. But let's prove formally that this is going to work. The idea here is that for every letter except the first, all copies of that letter will have been taken by the time we start processing that letter. Or in other words, I'm just going to say, we're going to call it a character C. So all copies of C will have been placed in our answer string by the time we start processing that letter. And the idea here is that the letter before C appears at least as many times as C does, and the first and C is the first thing we try to assign to that letter. So we'll always take all copies of C before we reach C. And so what that means is that for any letter except the first, we're definitely going to end up with a valid assignment because we've already taken all the copies of C, and so there's no way that we're going to match C with itself. So the one case we have to worry about is the first letter, but in this case we know that that the first letter, which let's just say it's A, is going to appear at most n over 2 times. So there are at least as many non-A letters as there are A's. And so what that means is that we're definitely going to find enough other letters before we wrap around and we go to the A's again. So yeah, I'll show you my implementation. So first I just create the count of each letter in the CNT, and then I use this array ord, or I create this vector ord that stores counts and then the letter indices. So then I sort it and then I reverse it to get it sort in decreasing order. And I build our output string T, and then I iterate over each letter in order. I iterate over each letter of S, and if it matches, if it's the current letter, then I just try all the letters. This is how I sort of try everything after all the letters after I wrap around. I just start with I plus 1, and then I add K for 0 to 26. And then if that letter is still available, if the count is greater than 0, then I subtract 1 and I put it into T. Okay, problem B. Again, I think this is by far the hardest problem on the contest. I haven't rigorously proved my solution. I'm not going to go over everything in too much detail. I'm just going to try and focus on the intuition here. Okay, so again, try C and D first if you're having trouble with this. So to start, I'm just going to ignore the constraint that we have to start with a cut connected to the edge of the cake, and I'm just going to think about what we have to do if what we have to do in order to cut out the cake, or the delicious part of the cake. So let's say that we're trying to cut out a 3x4 square, let's say, and I'm going to try and draw that real quick. Actually, hold on, I'm doing this. Let's see. Okay, this isn't perfect, but it should be good enough. All right. And then I'm actually gonna need a different font. Okay. So first, let's just think about the case when k equals 1. Well, in that case, we can easily just do some math to compute the number of edges we're going to have to take. We're going to need to take all of these edges. And then for the interior part, let's say that this length is A and this length is B. Then we're going to need to take 2A plus 2B for the edges, because this edge has length A, this is length A, this is length B, this is length B. And then for the interior, we can show that we're going to need AB minus 1 edges. And the intuition here is that we're separating this out into AB squares. This whole thing is AB squares, and each of these little edges, each of these length 1 segments, is going to split, is going to disconnect 2 of these components. And so we start with AB components, and we have to keep disconnecting until we go down to 1 component. Or we start with 1 component, and we want to keep disconnecting until we get to AB components, and it's going to take AB minus 1 steps to do so. And so that handles the and so that's enough for the k equals 1 case. Once we handle once we handle the fact that the edges have to, or once we handle the fact that we have to connect the edges to the edge of the entire cake, which I'll talk about in a moment. But now, how do we extend this to the case where k is greater than 1? How do we take advantage of the larger squares? What I'm going to claim to you is that the best way to do this is essentially to split up the delicious part of the cake into k by k squares. So here, let's say if k equals 2, then we would split it up into these 2 by 2 squares that I'm going to highlight real quick. This 2 by 2 square, and then this 2 by 2 square, and then we have these leftover areas over here. And then for these k by k squares, we're essentially going to fill them mostly with length k segments, so where you can draw like this. So for example, if we draw like this blue segment, then this blue segment, then this blue segment, and then 2 segments here, and likewise for the bottom square. And then and then for the remainder, we can draw this blue line, this blue line, and then just a bunch of length 1 segments. But the general idea here is I don't want to go through all the math largely because it's just about to be midnight, and and so I do not have the energy. But the general idea is that we're going to split it up into k by k squares, and we're going to essentially try to draw length k segments along this pattern. And the intuition for why that makes sense is that it's going to maximize our ability to draw length k segments, which is going to be optimal. Okay. Now, what about the edges? So the first case we have to deal with is if any of the edges of the delicious part overlap with the edges of the cake. And if that's the case, then we can just subtract out the number of segments that we needed to cut off that edge, because in that case that cut already exists for us because it's on the edge of the cake. But if that isn't the case, which is the case in this first sample input, then we have to cut into we have to sort of cut our way in. And so what I do is I just compute all 4 cases where, like, for example, we can go from this point to this point, and then now we have to do this length 2 segment, but now we also don't have to do this length 1 segment anymore. And likewise, we can go from here to here in our initial cut, from here to here, or from here to here. And so I just try all of those 4 cases and see which one is optimal. So I'll show you my code real quick. So first I read in n, m, and k. I'm trying to index these in terms of like the corners of these squares, like these little intersection points, rather than indexing them by the squares themselves. And in order to do that, I increase n and m by 1, and I increase x2 and y2 by 1. So my initial answer just stores the length of the edges, or the ceiling of the, and so yeah, I'm storing and so in general, in order to cover a length of, for example, y2 minus y1 with segments of length k, that's going to take the ceiling of y2 minus y1 over k operations, and we can compute that ceiling by adding k minus 1 and then dividing by k using the typical floor division. And so then I compute the the length of the difference between the x's and the difference between the y's, and I add the area minus 1, just like I showed here. And so then we need to deal with the how we can add in more length k operations. And the way I do this is, so first I compute the number, or I compute, this actually, I guess I didn't really need these variables because they're the same as these two up here. But I compute the number of, or I compute basically the number of length k squares, or length k segments along the two axes rounded up. And then I subtract out the length 1 segments that we've used to connect them and add back the length k segments. I don't want to go over the math in too much detail because, again, that would just take way too long. But so I'd encourage you to work it out on paper if you're having some trouble following it. But I think the key intuition here is the idea of splitting into k by k segments. And so then I subtract out the edges if they overlap with the segment or with the edge of the cake, and if so, I say found is true, and that indicates that we don't need to sort of cut our way in. But if we do need to cut our way in, then I do some case where I try all four ways of cutting in and add in whichever way is going to be best. And as you can see here, these two represent like either going in like this way or this way. And so we add in the length we need to cut, but then we subtract out the length of this edge because that overlaps with the segment we've already taken, and then the similar idea for the vertical segments. Okay. Yeah, that's a tough one to explain in full detail, but hopefully the general intuition makes sense, and I'm happy to try and answer questions in the comments if you have any. But let's look at C. I think that one makes more sense. All right. So in C, we have this crossword puzzle, and we're given that every answer is a palindrome. And it's going to be partially filled in, and we want to fill it in as much as possible using only the fact that we know it's a palindrome. So let's think about sort of the overall structure of this sort of crossword. So every letter is going to be in one down clue and one across clue. And in a given clue, each letter is going to have to be equal to the letter in the opposite position. So for example, this B in this down clue has to be equal to this B in the across clue has to be equal to this one, and so on. And so what we can say, and so what we have is we have a bunch of constraints of the form, this cell must be the same as this other cell. For example, this cell here has to be the same as this other cell. And in particular, we have at most 2 of these constraints per cell. And at this point, we can start representing this as a graph theory problem. So the idea here is we're going to say the cells are edges, and then 2 cells are connected if the palindrome constraint forces them to have the same letter. And from here, we can just use a standard BFS flood fill algorithm to fill the graph in. And the easy subtask, by the way, is a simpler version of the same solution where instead of performing BFS, you just repeatedly iterate over the whole puzzle and fill in letters as you go. But I'll show you my implementation because there's still a lot of details to work out. So the first thing I do is I sort of pre-process the crossword. So what I'm going to do is I'm going to number all of the cross clues and all the down clues, much like in a real crossword. And these ACR and DOW arrays store the number of the across clue and the down clue that each of these letters is in, or each of these cells is in. And so I do that just by iterating over the grid. I skip the black cells, and then for example, if this is a continuation, or sorry, if this is not a continuation of a previous across cell, if it's either the first one in its row or the last one was black, then I start a new across clue, and otherwise it's the same across clue as the old one. Then PAC and PDO store the position within the across clue and the down clue, where so for example, this cell right here is the first in its down clue, which has length 1, and the second in its across clue. Then I store the total number of across clues and the down clues, and the number of letters in each across clue and down clue. So I maintain all of those variables, And then I'm going to store this queue, and I'm initially just going to push every letter that we already know. And then I'm going to do some math to figure out essentially the edges of this graph. So for example, if we look at the down clue, the idea is that the position that, so let's say that the down clue has length k, and our letter has position I, where again our positions are 0 indexed. Then we can do some math and figure out that the corresponding cell, the one that must be equal, must have coordinates k minus I minus 1 in the clue. Or so clue has length k, cell in position I, and then the matching cell has position k minus I minus 1. And so I find the matching position, and then I find the x coordinate at that position, and then I try to propagate the current letter into that cell if that cell is empty for now. And same thing for the across case. And for each cell I process, I increment the answer, I push it to the queue, and I just continue until there are no more cells that we can process. Okay. So the last problem is problem D, increasing sequence card game. So we have n cards, the ith card has the integer I written on it, and what we're going to do is we're going to shuffle the n cards at random, and we're going to repeatedly take the top card off the pile, and if the number on the card is larger than the number on the last card that we took, then we're going to take it, and otherwise we're going to discard it. So we want to find the expected value of the number of cards we're going to take. Okay. So this is going to rely on an idea known as linearity of expectations, and if you're not familiar with it, I would strongly recommend looking into it because it's pretty much the key to solving essentially every expected value programming contest problem. But here's the idea. So let's say that S sub I is going to be a random variable that's going to be 1 if we end up taking card I, and 0 if we discard card I. And since our score is the number of cards we take, we're looking for the expected value of S sub S1, or score for card 1 plus S2 plus S3 plus Sn. And this can be rewritten as the expected value of the sum, and I apologize, my sigmas may not be great, the sum over I equals 1 to n of S sub I. Alright. So the idea of linearity of expectations is that even though these variables may not be independent, we can shift the summation symbol outside of our expected value. That is, the expected value of the sum of several variables is the sum of the expected values of those variables, even if those variables are not independent. And so we're actually looking for, this is a terrible sigma, the sum over I equals 1 to n of the expected value of S sub I. And so that raises the question, how do we compute the expected value of S sub I? And so let's think about it like this. When do we take card I into our hand? The answer is that we take it whenever whenever every card, or the highest card we've taken so far, is smaller than I. So in other words, if any card, okay, I'm gonna write this out on my text editor actually. So when do we take card I? If any card before, I guess first of all, a quick observation is that the last card we took will always be the largest card that has appeared so far, and this can be proven inductively. Also fairly quick to observe. And so the idea is that if any card from I plus 1 to n has appeared already, then we discard card I. If all cards that have appeared so far are less than I, then we take card I. So given that, we take card I if card I appears before cards I plus 1 through n. And so that means card I must be the first of cards I through n. And so this gives us n minus I plus 1 cards, and then card I must be the first. And all of these cards are equally likely to be drawn first. So we take card I with probability 1 over n minus I plus 1. And so that means that E of the expected value of SI is equal to 1 over n minus I plus 1. And so this summation becomes the sum of 1 over n minus I plus 1. But if we transform I into n minus, if we reindex this into I goes to n minus I plus 1, then we can verify that this becomes the sum of 1 over n. And this is simply the harmonic sum, which you'll likely be very familiar with. This comes up a lot in complexity analysis, just because the harmonic partial sum has size about n log n, and so a lot of the time you'll end up with programs where this form, or that have complexities of this sort of form. Or sorry, this summation is log n. Oh wait, hold on. Sorry, this should be 1 over I, not 1 over n. So this sum, if you're curious, the reason that it's important is that this thing is log n, and a lot of the time you'll end up with programs in various problems where its complexity can be written in terms of the summation, and so that's why it's a good property to know. But anyway, in this case though, what we need to do is we need to actually compute this summation efficiently. So this gets us the medium subtask, because you can just compute this via brute force when n is up to 10 to the 6th. The small subtask, by the way, you could have gotten without all of these observations, just by iterating over every possible shuffle. But for the large subtask, we're going to need to handle this efficiently. And there's no closed form expression that we can use to get this summation. But we only need to get within an absolute or relative error of 10 to the negative 6th power. So we just need a good approximation. And I did not know a good way to approximate harmonic partial sums off the top of my head, so I Googled it, and Wikipedia gave me the following approximation. So, start a new page. Let's copy this, and let's see. I should have just drawn it again. So this sum is approximately equal to the natural log of n plus, okay, you're gonna need to forgive me for not really being a gamma drawing expert, plus gamma, plus 1 over 2n, I'm actually gonna need another line here, minus 1 over 12n squared, plus 1 over 120 n to the 4th. And in particular, this last term here is also a bound on the error. And so for sufficiently small values of n, this might not quite be accurate enough. In particular, like when n is 1, for example, then you end up getting gamma plus 1/2 minus 1/12 plus 1/20th, 1/20th, and it's pretty accurate, but it's not accurate, and in particular, it's accurate within 1 over 120, but may not be accurate to the 1/1 millionth ratio that's necessary. So what I did is I just brute forced when n was small. In this case, I used n less than 10,000, but you could actually use a much smaller bound. Like I think even like brute forcing when n is up to 10 would work fine. And then when n was large, I used this approximation. So yeah, that's a contest. Let's see what the scoreboard's looking like now. It's like there are 10 AKs so far, with B large being the strongest bottleneck by far. Only 16 participants in the first hour 45 minutes. So yeah, I think that's all I have. Please feel free to leave questions in the comments section if you have any. And otherwise, I will see you all next time.